In the quiet structure of a binary tree, every level tells a story, every node adds a voice, and somewhere among these lies the greatest sum. We move step by step, level by level, seeking not just a maximum value, but the exact depth where it truly belongs. Welcome to this presentation on the problem titled Maximum Level Sum of a Binary Tree. In this problem, we take a structured journey through a binary tree, moving level by level to discover where the maximum contribution lies. Our focus will be on understanding the problem clearly, identifying the right traversal strategy, and implementing an optimal solution with confidence. Let us begin by understanding the problem. We are given the root of a binary tree. The root node is considered to be at level 1, its children at level 2, and this pattern continues downward. Our task is to compute the sum of node values at each level and return the smallest level number whose sum is the maximum among all levels. In simpler terms, the problem asks us to traverse the tree level by level, add up the values of all nodes that appear at the same depth, compare these sums across all levels, and finally identify the level with the largest sum. If more than one level has the same maximum sum, we must return the smallest level number, making the ordering important. Let us understand this with an example. We are given a binary tree where the root value is 1. At level 2, we have nodes 7 and 0. At level 3, we have nodes 7 and -8. Now let us compute the sums. Level 1 sum is 1, level 2 sum is 7, level 3 sum is -1. The maximum sum occurs at level 2, so the correct answer is 2. In the second example, the tree contains both large positive and negative values. When we compute level-wise sums, level 1 gives a sum of 989, level 2 gives a sum of 10250. Level 3 results in a smaller value due to negative contributions. Once again, the maximum sum is found at level 2, which becomes our answer. This example highlights the importance of properly handling negative values. Now let us look at the constraints. The number of nodes can be as large as 10 to the power 4. Node values can range from -10 to the power 5 to +10 to the power 5. These constraints tells us we must handle negative numbers carefully. The solution must be efficient. Deep recursion may be risky, so an iterative approach is safer. The key insight is that this is a level-based problem. Since we need to process the tree one level at a time, the most natural and efficient approach is breadth first search or BFS. BFS processes nodes level by level automatically, which aligns perfectly with our requirement. We might wonder whether depth first search can be used. While BFS is possible, it requires extra data structures to track level sums, additional bookkeeping for depths. This makes the solution more complex and less intuitive. BFS, on the other hand, is cleaner, simpler, and purpose-built for this type of problem. At a high level, the algorithm works as follows. Push the root node into a queue. Start processing from level 1. For each level, process all nodes at that level. Compute the sum of their values. Track the maximum sum seen so far. Update the result whenever a higher sum is found. Finally, return the level number associated with the maximum sum. Here is how this works in practice. The queue size tells us how many nodes belong to the current level. We process exactly that many nodes, sum their values, and push their children into the queue. This guarantees clear separation between levels, accurate level-wise sum calculation. The pseudocode reflects this logic clearly. We initialize a queue with the root, a level counter, a variable to store the maximum sum, a variable to store the answer level. We iterate until the queue is empty, processing one level at a time and updating the result when a better sum is found. Now let us look at the actual C++ implementation. In the first part, we define the solution class, initialize a queue for BFS, push the root node, initialize variables to track the current level, maximum sum, and answer level. We also use long to safely handle large sums. In this part, we perform the BFS traversal. While the queue is not empty, we determine how many nodes belong to the current level, initialize the current level sum, process each node adding its value to the sum, push left and right children into the queue. This ensures all nodes at the same depth are processed together. After computing the sum for a level, we compare it with the maximum sum seen so far. If it is greater, we update both the maximum sum and the answer level. Finally, once traversal completes, we return the level with the maximum sum. This algorithm is correct because BFS guarantees strict level by level traversal. Each level's sum is computed exactly once. We update the answer only when a strictly larger sum is found. This naturally preserves the smallest level number in case of ties. Hence, the algorithm always returns the correct result. The time complexity is big of n because each node is visited once. The space complexity is also big of n due to the queue, which may hold up to one full level of nodes. This is optimal given the problem constraints. To conclude, this problem is a textbook application of breadth-first search. BFS makes level-based aggregation simple and reliable. The solution is efficient, readable, and optimal. Thank you for your attention.